Right now, in the time it takes to blink, hundreds of trillions of ghostly particles have already passed through your body. They slip through your eyes, your bones, even the Earth itself, and almost never leave a trace. They don't burn, they don't push, they don't even slow down. If you could see them, it would look like a storm raging through everything, every second of every day. These are neutrinos, invisible messengers from the heart of stars, from the most violent explosions in the cosmos, and from the first seconds after the Big Bang. They are the most elusive particles known to science, yet they never stop streaming through us. The name neutrino means little neutral one, first proposed in 1930 by Wolfgang Pauli as a desperate solution to a mystery in nuclear decay. The particle seemed almost impossible to prove. For decades, it was only a ghost in theory, until Frederick Rains and Clyde Cowan finally detected it in 1956, using a massive underground detector near a nuclear reactor. That discovery earned Rains a Nobel Prize, and it opened a new window into physics. Neutrinos are unlike anything else. They carry no electric charge, they interact through only the weakest of forces, and their masses are vanishingly small, less than 1/1,000,000th that of an electron. In practical terms, that means they barely acknowledge the existence of matter at all. A block of lead, a light-year thick, would still let most of them pass straight through. And yet, they are everywhere. Trillions pass through every square centimeter of your body, every second. For every proton or electron in the universe, there may be billions of neutrinos. They are the second most abundant particle in the cosmos, after photons of light. Where do they come from? Most of the neutrinos reaching you right now were born in the sun. Every second, nuclear fusion in the sun's core produces an unimaginable flood of them. Billions of billions racing outward at nearly the speed of light. If the sun suddenly went dark, light would take 8 minutes to vanish from our skies. Neutrinos, however, would reveal it almost instantly. They escape the sun's dense core long before light does, carrying the first warning. But the sun is only one source. Nuclear reactors on Earth generate intense streams of neutrinos as well. In the wider cosmos, when a star explodes as a supernova, neutrinos are the first signal to escape, carrying away more energy than the explosion's light itself. In 1987, detectors around the world captured 24 neutrinos from a supernova in the Large Magellanic Cloud, 168,000 light-years away. That brief shower confirmed that neutrinos are not just theoretical messengers, but real signals from dying stars. When two neutron stars collide, the torrent of neutrinos may be so overwhelming that it reshapes matter itself, forging heavy elements like gold and uranium. And beyond all of that are relic neutrinos, the oldest in existence. They were born in the first seconds after the Big Bang, nearly 14 billion years ago, and even now they drift through us, a fossil imprint of creation itself. If neutrinos were only invisible, they would already be strange, but they carry another secret: they change identity as they travel. Neutrinos come in 3 flavors: electron, muon, and tau. Yet as they move through space, they can switch from one to another, like a phantom changing masks mid-flight. This phenomenon is called oscillation, and it solved one of the biggest puzzles in 20th century physics. For years, scientists noticed a problem. The number of neutrinos coming from the sun was only about a third of what theory predicted. Was our model of the sun wrong? Was physics itself incomplete? The mystery, known as the solar neutrino problem, was finally solved when detectors confirmed that neutrinos were not disappearing, they were changing flavor. A solar electron neutrino could reach Earth as a muon, or tau neutrino, slipping past the instruments designed to catch only one type. This discovery was so important that it won the 2015 Nobel Prize in Physics. It proved that neutrinos have mass, something the standard model of particle physics had said should not be possible. The fact that they do forces us to admit that our most trusted theory is incomplete, and there must be physics beyond it. And new studies suggest that in extreme cosmic environments, like the dense flood of neutrinos inside a supernova. They may oscillate in collective waves, influencing each other in a grand cosmic dance. That means their behavior could directly shape how elements are formed in the universe. But how do we catch a particle that ignores matter? Neutrinos rarely interact, so scientists must build gigantic detectors just to see a handful of them. And because cosmic rays constantly bombard Earth's surface, the detectors have to be buried deep underground, underwater, or even under Antarctic ice to shield them from noise. In Japan, the famous Super-Kamiokande experiment sits a kilometer below ground inside a mountain. 50,000 tons of pure water are watched by 11,000 light sensors, all waiting for the faintest flash of blue Cherenkov radiation, the light that bursts out when a rare neutrino finally collides with a particle. In Canada, the Sudbury Neutrino Observatory once used 1,000 tons of heavy water to capture solar neutrinos, helping to solve the solar neutrino problem. At the South Pole, IceCube takes detection to another scale. It uses over 5,000 light sensors spread through a cubic kilometer of Antarctic ice, turning the continent itself into a neutrino observatory. When a neutrino strikes, the ice glows faintly blue, revealing the direction it came from. In 2013, IceCube announced the first detection of astrophysical neutrinos, particles from beyond our solar system. Since then, it has traced some back to distant blazars, galaxies powered by supermassive black holes. And now, in the deep Mediterranean, the KM3 NET telescope has begun operations. In early 2025, it recorded a neutrino with an astonishing energy of 120 quadrillion electron volts, about 30 times higher than anything humans can produce in a particle accelerator. Its source is still unknown. Did it come from a supermassive black hole, a galaxy in collision, or some cosmic engine we have yet to imagine? As impressive as detection has become, one of the most fundamental questions remains unanswered. How heavy are neutrinos? We know they must have mass, because oscillations would not happen otherwise. But their weight is so small that even today, we can only set upper limits. The Katrin experiment in Germany, a vast machine designed specifically to probe neutrino mass, has recently set the tightest limit yet. The electron neutrino must weigh less than 0.45 electron volts. For comparison, an electron itself weighs more than 500,000 electron volts. That means neutrinos are lighter by a factor of at least 1,000,000. Yet, in cosmology, even this tiny weight matters. Neutrinos, despite their ghostly nature, may account for a small but significant fraction of the universe's total mass. The mystery goes deeper. Which neutrino flavor is the heaviest, and which is the lightest? This is called the neutrino mass hierarchy, and solving it is a major goal of new experiments. In China, the Jiangmen Underground Neutrino Observatory, or JUNO, has just begun collecting data to measure this ordering. By comparing how reactor neutrinos oscillate, JUNO could finally tell us the hidden pattern of neutrino masses. Unlocking this secret could reshape our understanding of both particle physics and the early universe. Why spend decades chasing such elusive particles? Because neutrinos are not just shadows, they are keys. They carry information that no other messenger can. Light can be trapped inside a star's core, but neutrinos slip out almost instantly, giving us a direct view into processes otherwise hidden. In 1987, the burst of neutrinos from a supernova reached Earth hours before the light did, confirming theories of how stars die. One day, a similar detection could give humanity an early warning of a supernova in our own galaxy. Neutrinos may also answer one of the most profound questions in science: why the universe exists at all. In the first instance, after the Big Bang, matter and antimatter should have annihilated each other completely, leaving behind only radiation. Yet, for reasons still unclear, a tiny imbalance favored matter, and everything we see is built from that small excess. Some theories suggest that neutrinos, through a process called leptogenesis, could have tipped the scales. If true, Then without neutrinos, there would be no stars, no planets, and no life. The hunt for answers continues. In Japan, the next generation Hyper-Kamiokande detector is under construction, 20 times larger than its predecessor, with a volume of water big enough to catch thousands of neutrino interactions. In the United States, the Deep Underground Neutrino Experiment, or DUNE, is preparing to use enormous liquid argon detectors to study neutrinos fired from a particle accelerator 1,300 kilometers away. These projects will test whether neutrinos and their antimatter counterparts behave differently, a clue that could explain the cosmic imbalance between matter and antimatter. At the same time, neutrinos are entering a new era of multi-messenger astronomy. By combining their signals with gravitational waves and light, scientists can now study cosmic events from multiple angles, building a fuller picture of the universe's most violent explosions. Already, they have been traced to blazars, active galaxies with jets pointed directly at us, proving that these invisible travelers can reveal the hidden engines of distant galaxies. So the next time you stand in the sunlight, remember this: light is not the only thing our star sends us. An invisible river of neutrinos is flowing through your body, through the Earth, and out the other side, never stopping. Some of them were born just moments ago in the sun's core. Some carry the final heartbeat of dying stars. And some have traveled across almost the entire age of the universe, arriving here after billions of years in flight. They are silent, unstoppable, and eternal. Cosmic time travelers, whispering the history of the universe through every atom they pass. And with every new discovery, we are learning how to listen. If you enjoyed this journey, give it a like and subscribe to Scientific Facts, where the universe's mysteries come alive in every video.